Hi, welcome to part 3 of Computational Methods for Linguistic Typology. In this module, we're going to be looking at how we might formalize our assumptions and build computational models of our typologies in order to classify our data sets according to the variables of our typology in a way that is both rapid and iterable and reproducible. So in the previous videos, I introduced the typology workflow or the typological data science workflow, and we looked at identifying domains, acquiring data, building data sets, and sharing those data sets. Now I'm going to look at how we might formalize our assumptions so that we can automate the classification of our data sets into types. And this is really the crucial difference for these computational methods compared to traditional methods of typology. So what we've got at this point is a data set that we've coded up. We're dealing with inflected lexicons. That is computational representations of inflectional paradigms. Since we're interested in the typology of inflectional systems, that's the input. If we were interested in other sorts of linguistic phenomena, we'd be using distinct data sets for that. The data set we're going to be using is of this format. It's a bit more elaborated than some of the other ones we saw as examples because this is what some of the scripts that we'll be using will take as an input. The crucial elements here is you have the language name, right? Doculect. We have some kind of indicating the lexeme. We have the set of feature values representing the cell. Here they're separated into separate columns. We've got the form of the word, and then we've got a segmented form of the word. We'll talk a little bit about segmentation, but crucially that's the data set we're going to be using. If you look in the data folder on the GitHub, you'll see that there is this global touch paradigm of, I think it's something like 1200 forms or something at least. So how do we go from turning this into the type of typological samples that we saw in the previous slide where we looked at those output data sets? How do we go from our input data set, which is this, into a typologized collection of features? That's really going to be the topic of today's video. I'm going to be talking about this in respect to verbose exponents, which we already started to learn a little bit about before. So I'm going to just go through and take you through some of the domain of verbose exponents and then look at how we might formalize it, right? So there are lots of different types of verbose exponents. This is all based on a paper that that's just coming out in Morphology. And the sort of most common, certainly if you're talking about the phenomenon, people will say something like, well, that's multiple exponents. And so there is, fortunately, a wonderful book by Alice Harris on multiple exponents, where she goes through its typology and history and its relationship to theory. This is the definition that she provides for multiple exponents. That is, multiple exponents is the occurrence of multiple realizations of a single feature or bundle of features or derivational category in more than one position in one domain. So we've got multiple realizations, that is multiple forms of a feature or bundle of features, right? In more than one position, that means pretty much the same thing as multiple realizations, and within some domain. So this is only various interests depending on the domain you're looking at, and we're going to just stick to the word domain for the purposes of this project, but that it's very interesting to look at it at various domains. And the example she provides to illustrate this is taken from Batsby, a Nak-Dagestanian language from northeast Georgia. And in Batsby, you have verbs, these complex verbs that agree with their absolutive arguments and specifically in gender. So this is a gender 2 noun. And you'll see here it has these Y markers here that reoccur multiple times, each one agreeing in gender and here agreeing in number, although we'll see that's slightly more interesting case here. But you've got these identical markers. Here they're identical in form, but as we'll see, that's not a necessary definition of multiple exponents. So that's how people talk about multiple exponents. But there are a range of other clustering phenomena that seem similar to multiple exponents, but which are typically excluded from the typology. One of these is called distributed exponents. So here's the third person present forms from Nen, a Yam language spoken in the southern New Guinea region, Western Province PNG. And here's the forms of be erected, the third person present. And we might ask something of this paradigm, such as what is the exponent of plural? And here we have Well, you'll see here this word yatromger. The ya here at the beginning, well, it's clearly marking plural because it contrasts it with singular and large plural, but it doesn't contrast with dual, right? So it's on its own, not a plural marker. Similarly, the suffix ngr, here it's contrasting it with dual, but it doesn't contrast it with singular. So we end up saying something like the exponents of plural in the word yatromger is distributed over the prefix and the suffix, right? So this is something I've been calling distributed exponents. And you can see here, whilst it's not exactly the same as multiple exponents, it is quite similar. And we might want to include that in a typology of multiple exponents, I would argue. Well, similarly, here's the paradigm that we saw in the last class, in the last module, the first person present forms of a yay, a language very distantly related to nen, yimdede, to be sitting. So we might say, well, what's the exponent of plural here? Well, in this case, of dual, in this case, there is a dual marker, but in order to correctly, a speaker to correctly inflect a form for dual, whilst we have a dedicated dual marker, they also need to make sure they put in this non-singular marker here. So whilst there is an exponent of dual here, we might not say this is multiple exponents since these are slightly different distributions. It's still something similar, right? You've still got number being marked in multiple places. So this is the phenomenon that I call verbose exponents. It includes multiple exponents, but it also includes these various other cases, right? In the previous class, we defined it as the exponents of a category requiring more than is strictly necessary. But here we might define it slightly more formally, right? Slightly more explicitly. We might define it as two or more co-occurring formatives, which both provide some information about a feature in more than one position in one domain. So this is based on, obviously, the multiple exponents definition. But here we've got two formatives which provide some information about a feature. So that's the really crucial thing here, right? This becomes our slightly more updated base than when we started with, but one which we still haven't formalized yet. In order to formalize this, we need to go through and work out what are all of our assumptions here, right? We need to define our assumptions. And this is really a crucial part of formalization. And we need to formalize before we can do any sort of automation. So here we have the things we might need to formalize. We need to know what is a formative, right? We've got two or more co-occurring formatives. That's something we need to answer. What is a feature, right? Providing information about features, right? We need to define that, right? What does it mean to provide some information? And what is the relevant domain we're looking at? These are all the elements that we're going to have to formalize. Some of these might be based on assumptions, and that's fine for making progress in our research, but we need to come up with a definition for them, or at least a means of being able to handle it. That's irrespective of whether we're doing computationally enhanced typology or traditional typology. And I said, this is based on my paper. Here's the reference. If you're interested, please have a look. Let me know. And so in order to define all of those assumptions, we're going to start with introducing some set theoretic notation, right? We're going to just make some formal definitions of all of our assumptions, right? In order to get at that, what we're going to do is we're going to start with words, right? Words we're going to assume are the basic elements of our model. And we're going to define words as involving three components, right? They're going to compose of a word form, which we represent with a capital W, a cell, which we represent with a capital sigma, and a lexical index, which we represent with an L here. So these are the three components of a word. So for instance, our word nimdedane, taken from our yay, the dual marker, the dual form, has three component elements. It has a word form, which here we're treating simply as a string of phonological segments, of course. And this model is, agnostic. It can be as complex a phonology as you might have in there. It involves a cell, which is simply a set of feature values to describe the grammatical distribution of this particular word. Right? And here by word, I mean an individual inflected word. And there's a lexical index. These are all yimdede. These all belong to the paradigm of yimdede. And you notice this is exactly the type of, our basic model here matches the input data from our data set, right? Here's a simplified version of our data set of an inflected lexicon, right? where you have yay, you have the lexical index, you have the word form, and you have the cells. As I said, each of these can be as complex as need be. For the lexical index, maybe you could have structured features as well to capture structured lexicon. You could have multiple tiers in your word form, syllabic information, tonal, suprasegmental, all of those things. It's up to you how, it's up to the domain you're looking at, that you, based on your base, how elaborated you decide to make these. Of course, the more detail that are in your inflected lexicon that you don't necessarily need to use, but the better your data sets are going to be. So I'm just going to assume for now, we're just going to assume lexemes are just lexical indexes are simple because they're not really relevant for the typology of verbose exponents. We're just going to have lexemes. And similarly, we'll talk a little bit about the structure of the word forms in a moment. But before that, let's talk about cells. What does it mean to say that this is a first dual present? And how do we establish the features that are there? So this is obviously a crucial, an ongoing challenge in morphology, right? How do we determine a set of feature values? Well, and there are a range of different approaches, but what's crucial here is you set up your assumptions explicitly to begin with, right? For our model, and I think it's fairly well, and we can then argue about the terms, and if you, we can just get in contact with me if you, or talk in the comments about any suggestions you have about this, but we're going to use the type feature value, right? Sigma V, which is just a way of representing features with sigma, values with V. So features represent the dimensions of the paradigm, and the values represent the maximum distinctions for a given feature. So, you take all of the mutually exclusive distinctions along a single semantic parameter, such as number, and for all of the individual discrete forms, we use one single feature value for that, right? So rather than trying to capture syncretisms as shared feature values, we use, for our model, what we're going to be using, because we're interested in the information, is using a maximally distinguished feature model. So we'll take a look at our paradigm and see, okay, across the various types of number, at the level of the fully inflected word, there are three number values: singular, dual, and plural. And we just have a little function here which maps all of the feature to its set of values. So here, the values of number are singular, dual, and plural. And that's just necessary for part of the formalization later on. So we've established now what it means to have a cell. And we've taken for granted the lexical index, and we'll talk a little bit about word forms in a moment. Right? We can use this basic model, right? So now we have a model that has just two things declared. It has words, and as part of that, there are feature values. We can then use this to define a paradigm, right? We might define a paradigm as the paradigm of some lexeme, right? The lexical index is all the words for which the lexical index is that particular lexical index. So this just is a formal statement that says paradigm is all the words which share a lexical index. So a paradigm is all the words of a lexeme. So for instance, we can look at this with respect to our yay data. Well, so if we take the paradigm of yimdada, well, we get wumdada, nimdadane, nimdada, and then all of the other forms. There are about 600 of them. And you'll notice again that this ends up being basically the very related to our data set, and I'll let you explore that on your own. We can then make more and more complex statements about some data, right? We can say, well, we can talk about the distribution of some formative A in a paradigm lambda, so just some paradigm, so we can say that the distribution of A are all of the cells of the words such that the words are in that paradigm, and that formative is within that word form, right? And by formative here, we're just talking about some substring of that phonological string. Remember, we're defining word forms as a string of segments. So we just pick some segment, and if that word form contains that segment, as long as it's the equivalent segment that is a formative, it's all of the words. So this is just another way of saying the distribution of a formative is all of the cells where that formative occurs, right? So we might say, well, the distribution, so what's the distribution here of, say, our ne, prefix. So we can say the distribution of ne is the cell first dual present, first plural present, and then so on. All of the because the ne occurs in three of the 5 tenses, so it would list all of those. So we can make these statements about it. However, a quick note about segmentation. How do we know that this ne is really the same ne as that one, right? So that's a non-trivial problem, an unsolved problem, one being worked on currently by Sasha Benjamin, and there's this paper by Sasha and his colleague where they identify, where they look at how do you really say that this particular segment is the equivalent to the same one, right? How do you identify formatives? Our model so far, and how we're going to treat it today, is we're going to assume segmentation. Remember I said in the data set we had it pre-segmented. We're going to assume segmentation as provided by the original descriptions, but ultimately what we want to do is we want to be working to the state where we don't have to, we can work more closely with the data, so we can establish this algorithmically. But ideally what you would want is you want to be able to handle this as part of the model itself. But we're just going to brush that aside, and I encourage you to look into that as well. Right? So this is our data set, right? We've got, so this is just what I was saying, that we're going to use a pre-segmented form, and so that the segments have both the phonological form but also the position in which the word they're in pre-established. Okay, so now that we've got that, we can start to make even more precise statements. So we can talk about paradigms, we can talk about the distribution of a given formative across a paradigm. We can now say, well, what's the distribution of a given form across a paradigm with respect to some feature? Say feature sigma. We can say, well, it's all of the values, the values from the set of values in the language within within the distribution of that formative, right? The distribution of a formative with respect to a feature is the set of values of that feature from all the cells in its distribution, right? So to be more precise here, we can talk about the, remember we established the distribution of ne from yay as first dual present and first plural present. So we can talk now about the distribution of ne with respect to number as being dual and plural, right? So it's the two number values that it has, right? So we can now start to make more and more precise statements about this formative ne, right? And so you can see how I'm building up to this, right? Next, we can start to talk about informativeness, right? This was one of our crucial things, providing some information about a shared feature. Well, what does it mean to provide information about a feature? Well, now we have an explicit model of how paradigms work. We can make a very precise statement of this. We can say something like, well, what information does ne tell us given this paradigm? If we hear ne and nothing else, well, we know that it's dual or plural because it's not singular, right? As a virtue of what it's not in some ways. What information about number does did have, the stem? Well, if we just hear that and we don't hear any other information, well, we have no information about number because crucially it doesn't make any distinctions for number. It occurs with all of them. So a formative only provides information about a feature if it occurs with a subset of the total values of that feature. So ne occurs with a subset of values of number, whilst did doesn't, right? And so we can define this formally, right? So the I sigma, of A, that is, what is the information with respect to some feature that A has? Well, it's all the values where the values are in the distribution of the sigma and when the distribution of A is less than the full set of values for that. So if it occurs with less than a subset. Another way of saying this is that it is the dis sigma A if dis sigma A is not equal to V, right? Or if it's less than V. So we can go through this formally and we can say, well, the information that ne provides about number, right, is dual and plural, whilst the information that did provides about number is nothing, right, because despite its distribution being all three values of number. And we can go through and we can do this for all of the formatives in this paradigm. So now we can make some incredibly precise statements. We know what it means to say we have what it means to provide information. Right? This is pretty cool. Right? We can be really explicit in our terms. So to summarize, that was basically our little model. So we now have a formal model of words, in which distributions are defined as sets of feature values, right? So we could say, okay, we can talk about the distribution of a given formative as a set of feature values describing that distribution. We can use this to define distributions of formatives across entire lexemes. And then we have a way of distinguishing between distributions and information. You can see that informativeness can be formalized as any distribution which involves a subset of all the possible distinctions, right? That is, if it makes a distinction there, right? And so now we have some incredibly precise terms. We can use this to construct typologies, but we can also use this to write programs in order to help classify our data with respect to our model. So we can so this is where this set of tools that I've just been working on, you can have a look at this. This is just something I put together on GitHub, mostly for this and for some research, and it will keep updating. It's called Pytomex. It's just Python scripts for the typology of morphological exponents. And you can just, it's on GitHub here, you can see this here. And it has a number of functions in there. And I'll show you how some of them work. So first of all, we just want to import it as PTM. And then we want to read in our Ngolable example data as a data frame Ngolable DF, right? So let's just run that. So we'll have to import pandas as well, naturally, to get the pandas library. And now we've got that loaded in, we can start to do some things. So we've got import Pytomex and pandas. Crucially, this is something that's in the Python library, so this will happen automatically. Pytomex is something that's not in the standard Python, and you just have to get it from GitHub and put it in a folder. But it has a number of functions. One of them is the Isigma function. And so we can say, we can use it to work out the Isigma of a particular formative. So we can say, well, what's the Isigma of undergoer number for the S prefix that occurs in position 2 for the lexeme touch for Ngolable? Well, we can run this. It tells us that it's a non-singular undergoer. So it gives us our number information. We can do things like, well, what does it tell us about aspect? Well, it tells us that it's either durative or perfective, right? I'm not going to go through the whole Ngolable paradigm, but you can see here, so what we've been able to do now is we can already go through a massive data set, and we can classify all of the features and values across the entire language. So let's I think we might even play with this a little bit more. So we might say something like PTM sorry, I'm just going to look up, I forgot what I called. So we'll do something that's called, well, let's leave it for now, sorry. We'll come back to this at the end. So my main point is by having our explicit set of assumptions built in, we now can agree, and we can discuss the terms of those. We can also use it to automate and to help us speed up our typologizing. Let's move on to the typology. So now with our set of assumptions and a model in place, we can start to do some typological investigation. So first thing we need to define is the base, right? What is it? What is the minimum definition that an example needs to count as before it's relevant, right? And since we're looking at verbose exponents, we'll call that, which we started as, our definition was 2 or more co-occurring formatives which provide some information about a shared feature in more than one position in a domain. So now we can define this explicitly in set theoretic terms using our model, right? So we can say a word, omega, is an example of verbose exponents. If and only if, and I'll just walk you through this, this isn't difficult to understand. There exists 2 formatives in a word form, in the word form of that W it should be, and there exists a feature in that language such that the information provided by one formative intersects with the feature provided another, and it is not equal to 0, right? That the intersection is not 0, it's positive intersection. So and then we can use this now to go through and classify any particular example that we get as either belonging as a point in our typology or not. So here is our, so going back to Butsby, remember had those repeated Y markers, and we had them glossed as gender 2 and here we have gender 2 and singular, right? So now we can check, well, is this really verbose exponents or not, given our set of definitions? Sorry, I apologize for that. Rather interestingly, whilst those Y's there are glossed as gender 2 and singular, that's not really what their distribution is, right? We know that they're gender 2 and singular by virtue of the controller being present. But if you just see the Y on its own, its distribution looks like this. It's used in gender 2 singular, sure, but it's also used in gender 3 regardless of the number. And it's used in gender 7s and 8 with just in the plural. What a fantastic language this is. It always blows me away. 8 different genders, different number marking, but only 4 different features. It's just 4 different forms. A really cool system. But now we can go through and we can explicitly check. We can say, well, what's the distribution of this one of these Y affixes with respect to gender? Well, it occurs in gender 2, gender 3, gender 7, gender 8. What's its distribution with number? Well, it's singular or plural. So then what's the information it provides? Well, the information it provides about gender, that is, if you just hear this Y, and maybe there's some noise going on, you don't hear everything else, but you just hear that yeah, and you know, well, it's got to be gender 2, gender 3, gender 7, or gender 8. That's information I know. But then if you're like, what's the information you know about number? Well, you don't actually know any information about number at this point because it's singular or plural. So you can you can leave that off. So under this set of information, under this set of definitions, well, remember that there are multiple of these ones. So if they co-occur, the intersection of the information they supply with respect to gender is that it's 2, 3, 7, or 8. But together with number, it's nothing, right? So we can take our definition here and we can check, well, does this match? Does this match? Well, in this case, it is a case of verbose exponents with respect to gender, but because it can't, if the intersection equals 0, it's not verbose exponents. This is not a case of verbose exponents of number, only of gender. Interesting. So now we can classify quickly and precisely exactly what it means to be an example of verbose exponents. Okay. Next, and now we're going to go through and we can see how we can define all of the points of our typology, right? So I'll go back for a second. This is our definition of verbose exponents. Well, what are all the areas which we might have possible domains of variation within this definition? Well, we could have variation in the types of formatives that are available. We could have differences in the type of features that are used, right? And we can have types of variation in the types of intersection. All right, I'm not going to talk about the different forms that occur in verbose exponents or the different features. Rather, I'm going to talk about the different ways in which the information interacts. And so the first one I'm going to talk about is multiple exponents, right? So the most simple way that these two can interact is if they just provide the identical information. So this is simply multiple exponents we might define more precisely as verbose exponents, in which the information provided by one formative is identical to the information provided by another, and that information itself is not nothing. It has to be some information for it to really be an interesting case of multiple exponents, right? You could say, you could leave this off, but then you would have, well, you know, all these cases of multiple exponents of no information, which is, I guess, true in a way. You got both of these provide no information about number, but it's not a very interesting case of multiple exponents, right? And we can go through and we can do the same sorts of checks manually that we did with the verbose exponents. And we can also see in this case that the information provided by Y for gender is equal to the information provided by the other. Similarly, for number, but again, it's empty, right? So we can now check with our definition of information identity, also known as multiple exponents, that it is multiple exponents of gender, but not of number. So again, we can quickly classify our data, right? Well, at the moment, we can't do it quickly. We have to do it painstakingly with this formal algorithm. Formal definition, sorry, not an algorithm. But we can see how that we can use this then to speed things up, right? We could talk about subset exponents. It's simply been the situation where the information provided by one formative is a subset of the other, right? Which we saw in terms of our net example, yay example, sorry, dual in yay. So we know that the information provided by ne is dual or plural. The information provided by ane is dual, right? We saw that already. Therefore, since ane, the information provided by ane is a subset of the information provided by ne, as we can see here, then this is a case of verbose of subset exponents, right? So we can do that, right? We can classify unambiguously that this particular example is of that, right? We can then go through and say distributed exponents. So this is a much longer definition, but it basically means all other types of non-empty intersection. Non-empty intersection, but which one is not the subset nor equal to the other or vice versa. So it just allows us to explicitly state. So we can look at, in our yay example, plural marking. Remember I already said that plural marking was distributed exponents. Well, the information provided by ne with respect to number is dual and plural. The information provided by with respect to number is singular and plural. The intersection of ne and is plural, right? Neither is a subset to nor equal to the other. So here we have a legitimate case of distributed exponents. So we have a very precise definition, right? One that makes fairly minimal assumptions, but which those assumptions are very explicit. So we might disagree with some of the assumptions, but you can't disagree with the analysis, right? And we can go through and maybe we can either argue and come up with a new set of assumptions, or we can adjust those assumptions and run those. So here we have a basic typology in terms of the types of intersections available. We've got multiple exponents, subset exponents, and distributed exponents. This is basic set interactions. It's not particularly complex. But the reason I'm bringing this up is to show you how you might then automate it, right? So what we can do now with that basic set of assumptions is we can build that model, right? We already have a model that provides the Isigma. Well, then we just need to spill that out over an entire paradigm. So what we're going to do is we're going to classify, we're going to use from within Pytomex the function classify for verbose exponents, the touch paradigm from Ngolombo. And we're going to save this as a data frame called VEDF, right? Verbose exponents DF. And we can look at this and we can see here, okay, well, we've got this word form from the Ngolombo data in Typenont, and it's the cell, right? Ngolombo is an extremely morphologically complex language. It's the first person actor, first singular actor, sorry, and second singular undergoer, non-pluractional future irrealis durative. So it's something like I will touch you once is exactly what this means. And for the value of future irrealis, we'll see that it's the prefix in the second slot nt, and the suffix in the first slot nt. So it's got nt at the beginning and the end, and it's a case of subset exponents with respect to future irrealis. Similarly, within the same word, notice these cells are the same here, right? So a single word can be classified for multiple types of verbose exponents, right? In this case, for durative, which is an aspect value, the same two forms are a case of multiple exponents, right? That is that the nt for tense, well, the future irrealis is a combination of tense and mood, whilst aspect is its own value, it's a durative, and it's multiple exponents, and then so on and so forth. You've got here the same form is used for a different cell, right? And it has the same sorts of relations. So we can go through, and now we've got basically a classification of, we've got this Ngolombo paradigm with respect to our typology, right? And we can go through and we can explore some of this data. So let me get out of this. So now we can really quickly, I think this is super exciting, right? So we've just taken a data set and now we've already typologized it. In fact, how many examples have we typologized? Let's have a look. Well, it's 4,780 examples of verbose exponents in this Ngolombo paradigm. That's crazy, right? Imagine having to manually go through and do all of these calculations. Well, we don't have to, right? Remember we saw the syncretism database from Surrey Morphology Group, which was this beautiful multivariate database, and we looked for the language Amele, and it had the lexeme, and it had the form, and it had its set of features. That's essentially what this is, right? So we've taken our data set and we've turned it into that sort of output, right? But we haven't had to manually code up all of this data. We just coded up that data set. But we can ask so much more from that data set than just about verbose exponents. Not only that, we can do things like we can, let's play with this a little bit more. Let's have a look at this. Let's explore this data a little bit. We'll see that there are 646 different distributed exponents examples, 1,808 multiple exponents, and 2,326 cases of subset exponents. Right? The paradigm is massive. It's a massive paradigm, but remember, a single word might involve multiple examples of verbose exponents. Right? Let's look at how many unique word forms there are in this example. So there are only 91, right? Despite there being thousands of cases of verbose exponents, there are only 91 distinct word forms, right? However, some of those are recycled into multiple cells. There are 99 unique word forms in the paradigm, but 91 of those are examples of verbose exponents. So you can see here the extent of verbose exponents in the characterization of the Ngolombo paradigm. So we can quickly see how we can take a set of assumptions that we formalize, turn into something very precise that allows us to write a package like this, right? And I encourage you to get in and play with this package, see what you can get out of it. Send me anything you notice or any improvements or problems that you have, please, because I'm very keen to see, right? But you can see how not only can we, by writing this relatively simple script, go from a data set that we can completely classify with respect to verbose exponents in order to create the sort of output databases that we saw for say the syncretisms project, but we can by being able to do this, we can take the same data sets and reuse them for lots of projects. But we can always add extra granularity to our project, right? If we can come up with a new definition of types of interactions, right? We just have to add a few lines of code and we can rerun our entire typologizing and reclassify everything. We're just dealing with a data set that just has one paradigm from one language, but ultimately you would have hundreds of them, right? Thousands of rows of data, and you could reclassify everything together. Also, we might disagree about what it means to provide information. Maybe you have a theoretical assumption for some reason, some assumption that maybe it's distributions rather than subset distributions, which are really crucial for the types of information provided. Well, we can redefine the Isigma to work in a slightly different way, and we can retypologize the same set of data, and we can come up with competing typologies, which we can compare, contrast, and argue with. We can increase the granularity by increasing additional steps. We can say, well, really the typology has these extra things that are important, right? And we can also add, that's the vertical complexity, right? We can also increase it horizontally by just adding more and more data to this, right? And as we come up with more and more of these inflected lexicons for doing comparative work, we can constantly keep adding to our typologies quickly and rapidly. So I really hope that you can see the sorts of benefits of building the sorts of data sets that I was talking about in the last class. And hopefully you can come up with some cool ways how you can build formal models of typology to be able to really increase our typologies horizontally and vertically. So let's have a look at so with that in mind, I just have a few take-homes that I want you to remember. So the first one is that we're all aboard the train to Lake Baikal. There are two things here. The first is that we can use computers to make our typologies deeper, right, and wide, right? We can do the kind of fine-grained multivariate analysis, but in a way that is applicable to massive amounts of languages just by getting coded up data sets, right? We don't have to do one or the other. Also, crucially, that this is it's a destination we want to get to, right? But every step, any step along the way that you can take is valuable, right? So it doesn't matter if your next project, you don't have to do a fully automated typological project, but if you build some data sets and share them online, that's fantastic. Similarly, if you automate some of your data exploration process, excellent. So all of these are just one step at a time. Learn a little bit of Python, learn a little bit of statistics, and we just apply them one day at a time, right? The crucial thing here is that we're all on the train together. There's a typology workflow that we can apply to our projects, which is iterative and circular. It comes around and each step iterates on itself. Break things down into simple problems, but also be aware that each one feeds into the others and feeds back onto itself, right? Feel free to apply this sorts of thinking to your own project design. We can use automation to speed up the bottlenecks of linguistic typology, be that data gathering or even data for classification, like we saw with our verbose exponents example, right? Computers can really help with these things. We want to see data sets, right? We want you to think about how we can use automated processes to be building generalizable, applicable data sets that we can use a range of projects, things like inflected lexicons, things like cross-linguistic corpora. Think about what you can do with these, right? And we can use these to create the kinds of data sets, databases, which will be of massive interest to doing sort of distributional type studies where we look at the distribution of phenomena and the correlation between various phenomena. But we can use these to generate those regardless. So the data sets are really the crucial part here. And I want you to think about that. Think about how you might apply them to your own research. And finally, we've seen how explicit models of our typologies allow for these sorts of automation, right? Without an explicit model, it's a lot harder to define these. It's not harder, it's impossible to define some of these things computationally. And by having this model, we can agree and disagree on any of the assumptions, right? They're explicit. We can change those assumptions and retypologize our data and then compare the validity, compare the results. Which set of assumptions better classifies the data? And that's really what I want to leave you with there. I want you to think about how this data science workflow allows us to have these input data that we can classify, we can discuss, and we can generate our models. So thank you very much for paying attention. It's been a really long course. It's been really fantastic to put it together. I hope it's been of value to you. Please send me an email. You can find all my details online. Leave a comment in the YouTube if this is the way you want to do it. I'd love to hear what you think. Thank you very much for all your time. It's been great.